Hello dear student, today we are going to discuss one very important concept of electrostatics, that is Gauss Law in electrostatics. There is Gauss Law in magnetism also, but here we are just focusing on the electrostatics part, in which we are just first discuss about the statement of Gauss Law, its validity, what it is representing, what its significance, and how it will be useful in various applications in electrostatics, right? So let's first come to the statement part. So this is called Gauss theorem, and according to that, the total electric flux through any enclosed surface, closed surface or enclosed surface is the same thing, is equals to 1 by epsilon naught times of the net charge which is enclosed by that surface. Now here epsilon naught is what? It is called permittivity of the free space, and charge is Q. And according to the Gauss law, if we write down the flux, this phi is representing the electric flux. This phi is representing electric flux. And according to the statement, it says that it is 1 by epsilon naught times of the charge which is enclosed by that surface. So statement is this, that phi is equals to 1 by epsilon naught Q into Q, or you can simply write down as Q inside by epsilon naught. Q inside means the charge which is enclosed by that surface. I will discuss. And now you will say, sir, this is electric flux, but is there any other formula by which we can discuss apart from this Q by epsilon naught? Yes, there is another formula for calculating this electric flux, which is integral of E dot ds. Integral of E dot ds. They are putting this integral in this way. So you can say that flux will be E dot ds for the normal area. But when we are just putting this sign, that means we are calculating the flux through enclosed area. So this integral with this small circle will be showing that we are calculating the flux through enclosed surface. That's why they are writing that if you want to calculate the flux through the enclosed surface, what it will be? Closed integral of E dot ds. This is called closed integral of E dot ds, right? Now, I use some terms here like electric flux, E, ds. E is normally electric field and ds is the area. So now let me first discuss in detail about the electric flux, so that you will have the idea that what is this electric flux and what does it signifies. So in the next slide, so like electric flux, let's discuss about electric flux. It is represented by phi. I told you that we can define magnetic flux also, electric flux also. So for the ease, you can also write down this as phi suffix E. That means we are just discussing the flux due to electric field. What is this flux? It is the measurement of electric field lines. It is the measurement of electric field lines passing through a certain area. See, when we are talking about field lines, that is a hypothetical concept. You will say that lines are, but it is not visible. But they will be very, very helpful to visualize the influence or to get the feel of the influence of the electric field lines or magnetic field lines. So field lines will be a hypothetical concept which is giving you the visualization or the feel about that influence of the field, whether it is electric field or magnetic field. Similarly, we need to measure those number of field lines, how many number of field lines are passing through any certain area. So we are using the unit which is, we are using the term called electric flux, and electric flux will be basically the measurement of those field lines which is passing through a certain area, right? How it will be defined? The flux will be defined as E dot A. E dot A through a certain area, or you can also write down this as integral of E dot dA. E dot dA means it is the dot product of vector E and vector A. Oh, vector A. Area is a vector quantity. Yes, area is a vector quantity. Area is a vector quantity. Some of them are not knowing this thing. Area is a vector quantity. Yes, area is a vector quantity. You can see that. In fluids, you have studied that force is equals to pressure into area, right? How do we define the direction of the force? We define the direction of force by direction of area vector, not by pressure. Pressure is a scalar quantity. Pressure cannot give you the direction. Who is giving you the direction? Area. That's why whenever in the fluid and everything, when we are saying, okay, on this vessel, what is the force applied on this? We are always saying the force will be, the direction of the force will be defined by the area vector. So area is a vector quantity. Okay, think about more on this. Okay, that I will leave to you. You just see that. So area is a vector quantity. If area is a vector quantity, how we can give this direction of area vector? Suppose if this is the area. If I will say, what is this area? You know that if it is a rectangle, it is a into b. If it is a square, it will be a square. So value, you know that. But if I just interested in writing down this area vector, how do we give this direction of area vector? We will give the direction is always perpendicular to the plane. Always perpendicular to the plane of the area, right? So magnitude wise it is same. Suppose if this length is L, this length is B, we will say the magnitude wise it is L into B. But how to give the direction? Direction we will give by this vector which is perpendicular to the plane. Alright. Now, suppose through this area some number of field lines are passing. So suppose there will be field lines which is passing, and let us say this E is constant. So if this E is passing through like this area like this, then I will say that area vector as well as E both are in the same direction. And since it is the dot product of these two, so we know that A dot B will be AB cos theta. That means this value will be EA cos theta. If both E and A are in the same direction, what we will say? We will simply say that theta will be 0 degree. And that's why cos theta will be maximum, which is 1. And that is why the flux which is passing through this area will be E into A. That is also the maximum one. But what if the field lines are not perpendicular to the plane, if they are parallel to the plane? Suppose if this is some area and the field lines are parallel to this, then as I told you, area vector is given by this vector which is perpendicular to the plane, while E will be parallel to the plane. So what is the angle between them? 90 degree. That means now I will say theta is equals to 90 degree, for which my cos 90 will be 0. And the number of field lines which is passing through this plane will be 0. Now you will say, sir, there are field lines, but why you are saying 0? I am saying number of field lines passing through the plane. So actually the flux, when you calculate the flux or number of field lines, it is the number of field lines which is crossing that area. So here the maximum number of field lines are crossing the area. That's why it is E into A. But here no field lines are crossing. They are just grazing on the plane. They are not crossing the plane. That's why what is the flux? Flux becomes 0 only. Understood? So this is how we will say that if the lines are parallel to the plane, the flux passing through that plane will be 0. But if the lines are perpendicular to the plane, the number of field lines passing is maximum. Or you can say this is the number of field lines which is crossing. So flux basically define me the measurement. You can say, sir, you have chosen the area in this direction. What is the basis of choosing the area? Because you said that, okay, it is perpendicular to the plane, but I can also choose perpendicular to the plane in this way, that this area vector is also perpendicular to the plane. So why you have chosen the area vector in this direction, not in this direction? See, as far as we are talking about a certain area, the direction really doesn't matter much. Why? Because either you write down E into A or E into A. We can say, okay, it is going on the left side or right side. But this area vector will definitely going to affect your your flux when this area becomes enclosed. Because for a particular area, if you see from this side, it will be like, okay, the field lines are coming. If you see from this side, the field lines are going through this area. So this area vector can be anything. But if I am talking about enclosed area in the sense, let us say this is a cube. Let us say this is a cube and there is some field which is existing here. For this particular field, if I say, how do we choose the area for different portion? So I am just giving some different colors to these faces. Let us say this is my one face of this cube. Let us say this is the another face of the cube. I just named it as 1. I just named it as 2. Whenever it is an enclosed area, you have to always choose the area vector. Always choose the area vector perpendicular to the plane and outside. and directed outside the enclosed surface area. Means if I choose the area vector of this phase 1, then my area vector will be in this direction. If I choose the area vector for the second one, it will be always in this direction. Means it is going outward. If I choose the area vector of this phase 3, it will be outward. If I choose the area vector of this 3, it will be outward. So every time you have to choose the area vector for the enclosed surface away. For a certain area, for a cross-section area, you can choose anything because it is simply depending on the which side you are looking for. If you are looking from this side or left side or right side, it will be coming towards you or going away from you. But when it is the enclosed area, always the area vector you have to choose outward. So if I see in this case, let us say E will be directed from left to right, then for the phase 1, if I ask you what is the for the phase 1, what is the flux is there, then you will say, sir, E and A will be opposite, means theta is 180 degree. Can you see that? This is my A, this is E. What is the angle between them? 180. That's why if you say EA cos theta, then EA cos theta, it will give you the value cos 180 is -1. So that's why it will be minus E into A. Similarly, if I say what is the flux passing through the phase 2, it will be coming plus E into A because angle between them is 0 degree. So now for the enclosed area, we are getting the plus and minus sign also. Means if you see from the phase 1, the flux is entering inside the enclosed area. While if you are looking at the phase 2, it is exiting out. And this is giving me the sign convention also. So by this thing, you can also conclude that whenever I am getting the negative sign with the flux, what does it mean? The flux is entering. That means entering flux inside the enclosed area. Entering flux inside the enclosed area, you will always put it with the negative sign. Similarly, the exiting flux, the flux which is exiting out from the enclosed area, you always take it as a positive sign. Do you understand? So negative sign you have to choose for the flux which is entering inside the enclosed area, and positive sign you have to take for the flux which is exiting out from the enclosed area, right? You understand that thing? Okay, if I ask you what about the remaining 4 phases? Now see, for the remaining 4 phases, you can say, sir, since the field lines are going parallelly to the plane, whether you look at the top phase or the bottom phase or the front phase or the back phase, always the field lines are parallel to the plane. So for remaining 4, it will be 0. So this is how we calculate the flux. If it is crossing perpendicular to the plane, the flux is maximum. If it is parallel to the plane, it becomes 0. But as far as enclosed area is concerned, flux which is entering, though it is maximum, but it should be written with the negative sign. Why? Because it is entering. Area vector will be outward, E will be inwards. And the flux which is exiting out, E and A both will be outward. That's why it will be positive. So this convention is really very, very important, that positive and negative sign you have to choose accordingly as entering or exiting, right? What are the uses? So I hope that you understand what is the flux is. So electric flux is the measurement of the number of field lines, and how to calculate the flux by E dot dA or E dot A. If E is uniform, you can directly say EA cos theta. If theta is 0 degree, it will be maximum. The sign of the flux will be positive. If theta is 180 degree, again the flux is maximum, but the sign is negative. For the enclosed surface, you can simply say that flux entering will be negative and flux exiting will be positive. Okay, now let's move. What are the proof? So if I'm talking about the proof of this Gauss law, we are just assuming here that there will be a charge placed here, Q. Q charge is placed, and this is a spherical surface. The surface which is shown by the orange color, this will be a spherical surface, and here we are choosing one area dA, where the field is also there, which is E. So this field E at some distance R, this we can write down as 1 upon 4 pi epsilon naught into Q by R square. And if I multiply, if you see here, then E as well as area vector. I told you that for the enclosed area, how you choose the area vector, always outward. That means both the direction E and A will be outward, means 0 degree. So if you calculate the flux, see, we consider an element on the surface as ds, and when we are finding out the flux, we will write down E dot ds. For this E dot ds, the field is 1 upon 4 pi epsilon naught Q by R square, and for this ds element, For this ds element, what is the flux? It is E dot ds. In the next slide, you will see this E dot ds. E dot ds, I just put this value and ds. For this surface, we have chosen this spherical surface here. For this surface, this is the charge. This is your ds. This ds vector will be outward, as well as this field is also outward. As we have chosen this surface as spherical, so at every point you will find out the same field E. Means at every point the distance r is same as far as this sphere is concerned. As far as this sphere is concerned, right? At all the point of this sphere, you will find out the same field. So field is same as r is not changing. That's why in the entire expression, this kq by r square means 1 by 4 pi epsilon naught into q by r square. That entire thing is a constant. You have to do the integration of this ds only. And what is the integration of this ds? That is 4 pi r square. For the sphere, the surface area of the sphere is 4 pi r square. So clearly you can see that this 4 pi r square, 4 pi cancel, r square cancel. What we are getting? Q by epsilon naught. That means the total flux which is passing through this spherical surface will be due to the positive charges. As we have calculated, this flux is coming Q by epsilon naught. And the point to be noted, this is coming positive. Why it is coming positive? As we have discussed earlier, that the entire, due to the positive charge, the entire flux is coming out, and exiting flux is always having the sign positive. If it is a negative charge, the entire expression will change with the negative sign, and finally if it is a negative, q becomes negative. Then by the same process, what we are getting the flux as minus q by epsilon naught. And why we are getting this minus sign? Because in that case all the field lines are actually entering in the spherical surface. Do you understand? So now this is also supporting my sign convention, that if it is a positive charge, all the flux is coming out from the enclosed surface. That's why it is coming positive. And it is also supporting my sign convention. If it is a negative charge, all the flux is coming inside the spherical surface. That's why convention wise also it is coming negative. So either by Gauss law, it is also satisfy the statement of the Gauss law that the total flux passing through this surface will be q inside by epsilon naught, as well as the convention, sign convention of the flux. Now, if you see the previous diagram, I showed you two surfaces. One is a spherical surface and one is some random surface. So you can ask me that, sir, we have proved this thing for the spherical surface, that when we calculate for the spherical surface, I am getting q by epsilon naught. But is the Gauss law is only valid for the spherical surface, or for any random surface we can say that? Means what? Means suppose if there is any random surface and there is some charges q1, q2, q3. Can I say for this surface also that my total flux passing through this random surface will be equals to total charge inside divided by epsilon naught? The answer is yes. Though we have proved it for the spherical surface, but it is also valid for any random surface. And reason is what? Reason is that if I choose one random surface here, let us say there is some random surface which is enclosing this charge. The charge is, let us say, spreading some of the number of field lines. Let us say they are in numbers. Let us say 1000 field lines are coming out from this spherical surface. There will be no other charge in the vicinity of this random surface. That's why no additional field lines can be added or subtracted. That means the amount of field lines which is passing through this random surface is also the same. That's why if it is valid for this spherical surface, the same number of field lines is passing through this random surface also, and we will say the total number of flux passing through that random surface will be nothing but q inside by epsilon naught. You understand this point? So it is valid for the random surface also. If you calculate by the integration, it may be very complex, because every point you are getting different E in different direction, every point you are getting different ds. So different E and different ds will give you different flux. So mathematically it is quite complex to calculate, but theoretically, or you can easily visualize that if it is a measurement of the number of field lines, then whatever number of field lines which is passing through this spherical surface is the same number of field lines which is passing through the random surface. That's why Gauss law is not only valid for spherical surface, it is valid for any of the random surface. Any arbitrary surface you will choose, it will give you the same flux, q by epsilon naught. So this is the proof of Gauss law. Now what are the uses? See, we are talking about Gauss law in electrostatics. And when we are talking about electrostatics means we are talking about point charge or continuous charges or charge distribution, laminas which is having different charge distributions. So the main thing is what? That we need to calculate the influence of those charges, which will be calculated by electric field intensities and all. So there will be one method already we have, which is Coulomb's law, that due to any charge, the net field will be kq by r square at any point by using the Coulomb's law. If there is a distribution of the charges, let us say the charge is distributed over the line or over the entire lamina, then we can calculate the Coulomb's law using the superposition, using the integration, means using the complex mathematics. So by the Coulomb's law also you can calculate, but Gauss law will make it your calculation much more easier. So by the Gauss law, whenever there is a symmetric distribution of charges and we are interested to find out the calculation of electric field and flux, Gauss law is really very useful in those cases. For example, if I say that even for the point charge, suppose this is a point charge and I am interested to find out the field at this point, I will simply choose one Gaussian surface, a Gauss surface, and I will apply the Gauss law and easily we can find out the field at this point. Though it is, I am not going to drive it, but in broad cases it will be important. Similarly, if there is a line charge and on this line there will be charges, then in the surrounding there will be field. Now to calculate this field, either you have the Coulomb's law. If I say what will be the field at this point, by the Coulomb's law it will be really very difficult. Why? Because you will say, okay sir, at this point I have to choose one element dq, then I have to find out the field, and then I have to integrate for the entire charge, and then it will give me the net field. So by using the integration and complex mathematics, we will be able to get it, this field, using the Coulomb's law. But if I am using the Gauss law, it will be much more easier. So on these cases where the symmetrical distribution of charges are there, by using the Gauss law, it is much more easier to calculate electric field intensity. In this particular lecture, I am just going to discuss the validity of the Gauss law and related problems. So we are not focusing on the calculations of electric field using the Gauss law. In some other topics, we will discuss about it. But where it is important, wherever there is a distribution of charge which is symmetrical, using the Gauss law, you can make your calculation much more easier for the calculation of electric field intensity. Obviously, it is used for calculation of the flux, but for the enclosed surface, because as you know that we will, what is the statement? 1 by epsilon naught times of q inside. So Gauss law is valid for enclosed surface. That's why it is also helpful to calculate the total flux which is coming out or coming in through the enclosed surface. So this is also there. Third point is the same point as one, that it will be useful for calculation of electric field intensity for various kind of charge distribution. Symmetrical charge distribution, in some cases asymmetrical charge distribution also, but there will be a different approach for that. Okay, now let's come to the question part. What type of questions are there? So hopefully you understand the flux, how to calculate the flux, what is the area vector, how do we choose the area vector, direction of E and direction of A, when they will give you the maximum flux, when they will give you the zero flux, and for the enclosed surface, how to choose the sign convention. The flux which is entering will be always taken as negative, the flux which is exiting out from the enclosed surface is always taken to be positive, right? So now, supporting that, let's discuss the first question. It says a surface has the area vector A is equals to 2i cap plus 3j cap. So what is the area vector given? Solution. The given quantity, first note down the given quantity. What is the area vector? It is 2i cap plus 3j cap. While what is the field here? Field is 4i cap. And we have to calculate the flux. So if I am talking about the flux will be E dot A, or you can say E dot dA. You say, sir, every time you are writing two formulas, E dot A or E dot dA, when this will be useful? See, when E is constant, you don't need to think about integration part. You can directly use E dot A. Here you can see E is not varying. Its direction as well as magnitude both are fixed. So when it is a constant field, you don't need to think about this integration thing. You can directly say it is E dot A. E dot A means dot product of the two. So if suppose there are two vectors, vector A and vector B, and you have to do the dot product of them. when they are giving in the form of component. You will say, sir, it is AB cos theta. Fine, AB cos theta is also the correct formula, but that is when you know the values and angle between them. I am not looking for that. I am looking for when it is given in the component form, means mathematical expression. Then what is your A dot B? It is AX BX plus AY BY plus AZ BZ. So same way, if you can see that here area vector in E is given in the mathematical form, that means the flux I can directly say as E dot A, which is EX AX, EY AY, EZ AZ. So what is the x component of E? 4. What is the x component of area vector? 2. Plus, what is the y component of E? 0. What is the y component of area vector? It is 3. That's why it is giving you 8. Because second term will be 0. So 8 is the total flux, and unit of flux will be voltmeter. You can write down voltmeter or you can write down Newton per Coulomb meter square. Both are the same unit. See, E, what is the unit of E? What is the unit of E? It is force divided by charge. So Newton per Coulomb, and into area. So it is meter square. So both are the same unit. Voltmeter or Newton meter square per coulombs, right? So the correct answer is the first one, 8 volt per meter. Okay, let's move to the next problem. Now this particular problem is based on sign convention of the flux. We have discussed that for the enclosed area, the flux which is incoming becomes negative and which is outgoing is always positive. So here the inwards and outward electric flux is through the enclosed area. So there is some enclosed area for which they are saying there is some flux which is outward, and there is some flux which is inwards. So what is the inward flux? It will be 8 into 10 to the power 3. What is the outward flux? It will be 4 into 10 to the power 3. But we are missing something. What is that? The sign. As I told you, always the outward flux is taken to be positive. Always the inward flux is taken to be negative. That's why while writing down these flux, you have to take care of the sign convention. This is negative, this is positive. And therefore, if I say what is the overall flux which is passing through this enclosed surface, then we will simply add them with their respective sign. And that is why it is minus 8 plus 4 into 10 to the power 3, which gives me minus 4 into 10 to the power 3 is the net flux. According to the Gauss law, what we will say? We will say that the total net flux passing through any enclosed surface is equals to total charge inside divided by epsilon naught. Yes or no? By using Gauss's law. So using Gauss law, we can say it is total equals to Q inside by epsilon naught, and that is why what is your total charge inside? That gives as 4 epsilon naught into 10 to the power 3 is my final answer. So what is your answer? The answer is option D. Minus 4 epsilon naught into 10 to the power 3 coulombs. That will be the charge which is enclosed by this enclosed surface. Okay. So this is the question which is based on sign convention. Now let's move to the next one. The electric charge are distributed in the small volume. The flux, these all are related to the concept, because if you understand the concept of the flux, the concept of the field lines, you can very easily, there is no much calculation is needed. Only the concept is needed. Now see, the electric charge is distributed in a small volume. Let us say this is some small volume in which there is some charges there. Now they are saying the flux of the electric field through the spherical surface. Now they have chosen some spherical surface here, right, which is having the radius 1 meter. So through this spherical surface, what is the total flux passing? They have said that total flux which is passing through this spherical surface, I just give the name to this as 1. What is the total flux passing? 100 voltmeter. Find out the flux which is passing through the concentric sphere. Concentric sphere means there is another sphere which is having the same center, concentric. But this time the radius of the concentric sphere is 2 meters. So this is 1 meter, this is 2 meters. That means it is the inner sphere, it is the outer sphere. And they are interested to find out the flux which is passing through this. So I really don't need the calculation because the charge is in the small volume. Small volume means it is inside. That means no charge is there in the vicinity of these two spheres. Only the single charge is there. That's why the whatever number of field lines which are originating from here, they will be simply passing through the sphere 1 as well as the same number of field lines is passing through sphere 2 also, right? Because no other charge is there which is adding any number of field lines in between. So same number of field lines which is passing through sphere 1 is the same number of field lines which is passing through the sphere 2, and that is why my directly answer is that through the sphere 2 also the same number of field lines should pass through. So my answer will be C. 100 voltmeter means no calculation is needed, just concept. Understand? You can say, sir, this charge may be bigger also, but they clearly mentioned that it is in the small volume, means it is inside the sphere 1 as well as inside the sphere 2, means it is nearby, somewhere near to the center. Alright. So total flux across both the spherical surface becomes the same. Let's move to the next problem now. They are saying a conducting sphere S1 interacts a closed surface S2 as shown in the figure. A positive charge Q is placed at a point P. Okay, I just clarify this question first because they have not mentioned what is the point P. Let us say this is the point P. This is the point P, and at this point P they have placed some charge Q. And now they are asking what will be the flux which is passing through the surface S2. Okay. If I look into this problem, my direct answer will be okay. Through this surface S2, this is my surface S2, and according to the Gauss law, the flux which is passing through the surface S2 will be nothing but it is the charge which is inside divided by epsilon naught. So what is the charge inside through this S2? It will be total charge as Q. So my answer should be Q by epsilon naught. This will be my simple answer. But the question is having little twist. If this will be the case, if suppose if this sphere is not there, only one charge is there which is inside. What I mean to say, if this is the surface 2, this is the sphere surface 2, and there will be a charge which is placed here. Without any doubt, you can directly say the total flux will be Q by epsilon naught. But the thing is what? You have put the charge on point P, which is on the conducting sphere. And since this sphere is conducting, so what will happen? This charge will be distributed on the entire surface. Though you are putting it on the point P, but this charge will be distributed among the entire surface. So what will happen now? So if it is distributed to the entire surface, what will happen? Only this much charge will be inside. Only the charge which is on this arc will be inside for the surface 2, and this charge is definitely less than this charge which is on this arc will be definitely less than Q, because now this entire Q charge will be distributed over the conducting surface. So on this surface it will be only Q dash which will be less than Q, and if the charge will be less than Q, then for the surface 2, what is the Q inside? Less than Q. And if it is less than Q, what should be the flux? Less than Q by epsilon. So very conceptual question. You can simply say, as I will write down the explanation, as the sphere is conducting, which is sphere S1 is conducting, the charge is spread over the surface. So overall net charge Q dash enclosed by surface S2 is definitely less than Q, and therefore the flux which is passing through S2 will be Q inside by epsilon naught, which is Q dash by epsilon naught is definitely less than Q by epsilon naught, and my right answer should be C, not B. Understand? If there is a point charge, or if I will say, okay, the point charge will be placed on a non-conducting sphere, still it will be good, because non-conducting, the charge cannot spread. But since it is a conducting sphere, the charge will distribute over the entire surface, and that's why For S2, it is not the total charge Q which is inside it, which will be definitely less than that, and therefore my flux will be less than Q by epsilon naught. Okay, so again a very good and conceptual question. Okay, let's move to the next one. Okay, this question, again this is a line charge, a charge which is distributed over the line, and we are interested to find out the total flux which is passing through this cylindrical surface. So on this line there will be a charge given which is Q charge, Q coulombs per centimeter. Just look at the unit. It is per centimeter, the charge is Q. The per centimeter charge is Q. That means if I am looking for the charge which is inside the cylinder, only this much portion. Because whatever charge is there which is inside it, I am interested in this much of the charge, because by this cylindrical surface, what is the charge enclosed? Only this much portion. So if I say what is the charge which is enclosed by the cylindrical surface, you will simply say it is lambda into L, which is Q coulombs per centimeter into 1 meter. 1 meter means 100 centimeter. So this centimeter cancel, means 100 Q coulombs is the charge which is inside this cylindrical surface, and therefore by Gauss law we can simply say the electric flux which is passing through the cylindrical surface is Q inside by epsilon naught, which will be equals to 100 Q by epsilon naught is the right answer. Alright. So sometimes they will play with the unit, like here they are not giving you the charge directly, they are giving you charge per unit length. Using the length, you can find out the total charge enclosed by this cylindrical surface, and then again by using the Gauss law, you can calculate the total flux which is passing through this cylindrical surface. Okay, let's move to the next question. Again, one interesting question. Which of the following statement is correct? Gauss law is valid only for symmetrical charge distribution? No. It is, Gauss law is even valid for random surface, as we have discussed. For any arbitrary surface, it is valid. If the charge distribution is symmetric, my calculation of electric field intensity becomes more easy. So, for the ease of calculation, the Gauss law will be really helpful for symmetrical charge distribution, but that doesn't mean that it is not valid for any arbitrary surface. It is valid for any type of distribution of charge. Gauss law is valid only for the charge placed in vacuum? No. It is even if the charge is placed in medium, then also it will be valid, only the expression epsilon naught will change. The electric field calculated by the Gauss law is the field due to the charge inside the Gaussian surface. See, in the expression of Gauss law, you are saying the total flux is Q inside by epsilon naught. Q inside by epsilon naught. But that doesn't mean that the field is only due to the inside charge. It is depending on the charge inside. But whatever field is coming for that Gaussian surface, it is the overall field which is due to inside charge and outside charge. Then you will ask me, that sir, then why it is only depending on the charge inside, why it is not depending on the outer charges? Let's see. Suppose we have one spherical surface. Whatever is the charge which is inside, let us say Q1, then whatever number of field lines which is passing, I can clearly say the flux is depending on this Q inside. But what if the charge is outside? So suppose I have the same spherical surface again, and now the charge which is I am having outside. Outside charge will also produce the electric field. Yes, it will also produce the electric field which is passing through like this. But what will happen if you see through this portion of the sphere, there are some number of field lines which is entering, but the same number of field lines is then exiting out also from the remaining portion of the sphere. Can you see that? See. From this much of the portion of the sphere, there is some number of field lines which is adding, which is entering. And from the remaining portion of the sphere, the same number of field lines are exiting out. So even if I want to calculate the total flux due to the outer, whatever amount of negative flux which I have to add, the same amount of positive flux is coming out. That's why the overall net flux due to the outer charge becomes 0. So field will be at every point, the field will be the overall field due to the inside charge as well as outside charge. But in the calculation of the flux, the contribution of the outer charges will be 0, because whatever amount of entering flux is same is equals to the outer flux, and that's why in the contribution of the flux, the outer charge is not giving me any contribution. Only the charge which is inside it is giving me the contribution. That's why in the expression, when you are writing down the expression of Gauss law, you are only considering Q inside, because outer charge is not contributing in the flux. But the C point, the electric field calculated by is due to all the charges is due to the charges inside is wrong, because the field is due to overall charge, right? Flux is not due to the outer charge, but field is because of overall charge inside as well as outside. So C is also wrong. Now D, the flux of the electric field through the enclosed surface is due to all the charges. So flux of the electric field through the enclosed surface due to all the charges. So suppose if I say whatever is the total flux due to all the charges, whether it is inside and outside, it will be same as the field, the flux which is due to the inside charge. See, if I say there is Q1 and if there is Q2, if I say the total flux due to Q1 plus Q2, then it will be the flux due to Q1 plus the flux due to Q2. But since the flux due to Q2 is 0, because outer is not contributing anything in the flux, so that means we will say the total flux due to inner and outer will be same as the flux which is due to inner only. They always come same, because outer will always gives you 0 flux through the enclosed surface. So my correct option is D. So again, a very conceptual question and very good question. Okay, let's move to the next one. Okay, another interesting one. The charge Q is placed at the center of the open end of the cylindrical vessel. The flux of the electric field through the surface of the vessel. Okay, let me make this diagram a little more clear. This is a vessel with the open end, and charge will be at the center of the open end. So charge is here at the open end. And what we are interested, so obviously this charge will produce some electric field lines which is also passing through this vessel. So we are interested to find out the field lines, the number of field lines which is passing through this vessel. Now if you say, sir, we have the formula, and by that formula, which is integration of E dot dA, we can find out this flux. Then it is quite complex. Why? Because every point E is different, every point D is different. So mathematically, we are not going to solve it by using the integration. We will again solve this by logic. Think about it, that suppose if the same symmetrical vessel is there, and I just put it on the top of it like this. Okay, so two vessels are there now, one is below and one is above. Then exactly the charge will be at the center, and I can say the total flux which is passing through these two vessels is, by using the Gauss law, is Q inside by epsilon naught. So net flux through both the vessels will be nothing but Q by epsilon naught. Alright. If I take the same type of vessel and I say just put it over it, then clearly Q will be at the center. So whatever number of field lines which is passing, it will give me the total flux Q inside by epsilon naught, which will be Q by epsilon naught. Why? Because now it is enclosed by both the vessels, and since both the vessels are symmetrical, so the number of field lines which is distributed for the top half and lower half will be also same. And that's why through each of the vessel, what we will say? We will say the net flux which is passing through each vessel is nothing but half of this, which is Q by 2 epsilon naught. So without any other calculation, you can say that the net flux which is passing through the vessel is nothing but Q by 2 epsilon naught, and the correct answer is C. Understood? Okay, you put the same symmetrical vessel, it will give you the total. Now the charge will be enclosed at the center, so it will give you the equal amount of number of fields which is passing through the top half and lower half, and that's why through each of the vessel, or through the vessel which is our desired answer, will be half of that. Half of that means Q by 2 epsilon naught will be the answer. So answer is C. This is the last question. Again, based on the same sign convention thing, that there will be an entering flux and there will be leaving flux. Entering flux, how do we take it? Entering flux, positive or negative? The flux which is entering is always taken with the negative sign. So how much is that? Minus 6 into 10 to the power 6. Whereas the flux which is exiting, S plus, so it is 9 into 10 to the power 6, and that's why overall flux will be if you simply add them, 9 minus 6 is 3. So it is 3 into 10 to the power 6, which is equals to Q inside by epsilon naught. And that's why the charge which is enclosed by this surface will be 3 times of epsilon naught into 10 to the power 6. So exactly the same question, the question number 2 which we have taken, their overall flux is coming negative, here the overall flux is coming positive. Achha. This is also indicating that the charge enclosed will be, if the overall exiting flux is more, clearly the charge enclosed is positive. In the question number 2, we calculated the charge which is coming negative. Why? Because overall flux which is entering was more, right? So this way you can say the charge which is enclosed is positive also. Whereas in the previous, in question number 2, we have discussed the same type of question here. If you see, this charge is coming negative. Why? Because the total flux which is entering inside will be more, right? So overall charge will be negative. So this is it about Gauss law. I hope this will be helpful for you. All the best, guys.